So it's a great pleasure for me to be able to introduce Dr. Karolina Smeds, who is going to give our first tutorial on hearing loss and hearing aid signal processing, as John has already said. Karolina is ideally qualified to tell us about these things because of her background and experience. So Karolina has degrees both in engineering and in audiology, and a PhD in hearing aid technology, and has for the last 15 years or so been the founder and leading light in a research group, which is part of Widex, hearing aid manufacturer, now merged with Siemens and Sivantos to become WS Audiology. So Karolina has a very broad portfolio of experience covering hearing aid technology development, hearing loss as an impairment and a disability to be treated, and also has done a lot of work understanding the auditory reality that people actually have during their daily lives. So she has a lot of useful things to impart to us. And I will, at this point, be very happy to pass over to Karolina. And as John was saying a moment ago, we're not expecting you, Karolina, to look at the Q&A or answer questions as you go along. You may focus on your presentation. And over to you.
Thank you very much, Graham, for that very kind and ambitious presentation. I hope I can fulfill the wishes from the steering committee about what you want for today. See if I can get rid of some windows. I think I've already been very clearly introduced by Graham. I also wanted to add that I have an affiliation on 20% at the University of Nottingham, apart from the work that I'm doing on 80% in Stockholm, Sweden. I wanted to start a little bit to talk about why hearing is important, and this one. And I want to talk about social relationships. Humans are social beings, and for most of us, social relationships are involving talking and listening to other people. And it's an important aspect of being a human, I think. And it's important at all ages. But I would like to talk about a meta-study about social relationships and mortality that was presented some 10, 11 years ago. And it was interesting with that study because it actually made the news, at least in Sweden, and people started to talk about the research studies so central to us. And in this study, they looked at the mortality risk in relation to social relationships. And they looked at 148 papers, which had used various ways to measure social relationships. And they plotted the odds of decreased mortality based on different ways of looking at social relationships. So if they looked at the overall findings, they ended up with this really difficult to interpret figure of 0.4. When they looked at more complex measures of social integration, they ended up a little bit more than 0.6, and it's impossible to understand exactly what that means. So what they did was that they compared the implications of social relationships on mortality with other factors that we know have an impact on mortality. So if we look at the more complex measures of social integration, the third bar, and compare that to, for instance, quitting smoking, if you smoked 15 cigarettes a day or less, the effect is larger for the social relationship. The same is true if you stop drinking alcohol and you were drinking more than 6 drinks a day, which sounds a lot. It's also a larger effect than being physically active as compared to not being physically active. It's also a larger effect than to be obese or be lean, have a lower BMI. And it's also a larger effect than to use drug treatment for hypertension for people above 59 years. And the conclusion that the authors made was that the influence of social relationships on risk for mortality is comparable with well-established risk factors for mortality. And the headlines in the news in Sweden was that it's more dangerous to be alone and not have people to interact with than, for instance, to smoke. This is not a study that I don't know if I can get that word. This is not a study that mentioned hearing or hearing loss in particular, but hearing and hearing well is also related to dementia prevention, intervention and care. The Lancet commissions have produced reports in 2017 and 2020 where they looked at factors that can affect dementia, if you get dementia. And they in particular looked at what they call possibly modifiable factors. And if we look at those in early life, less education is a risk factor for developing dementia. In midlife, hearing loss is a risk factor for developing dementia, and it is an 8% increase in risk. And it's actually the largest of the potentially modifiable risk factors for dementia. Hypertension, alcohol, obesity, smoking, and so on comes here in this list as well. And they say that around 40% of the risks for dementia are sort of known and potentially modifiable. And hearing loss in mid and late life is identified as the single largest potentially modifiable risk factor. We don't exactly know how hearing impairment and impaired cognitive functioning and dementia, how they are related. It could be that they just have a common cause, or just that they have a common cause, so that there is a common cause related to, for instance, vascular disease that affects both hearing impairment and dementia or cognitive impairment. But there are also hypotheses for what else could be the reason why hearing loss has such an effect on dementia. And one of them is that the cognitive load that a hearing impaired person needs to use in daily life in order to cope because of the impaired hearing could affect the dementia. And it could also be that because of the changes that happens in the brain when you haven't heard for some time, that is also an implication for cognitive decline. Or it could be connected to the last study, reduced social engagement that leads to a lesser full life and increased risk of dementia. We don't know. And currently there are lots of, or at least some big epidemiological studies being done in this field to learn more about the relationship between hearing impairment and cognitive decline. And of course, it is a very interesting question if early treatment of hearing loss can delay cognitive decline and dementia. And that's a big research topic, but still we don't know if that is true. If we could sort of slow down the dementia development by using hearing aids, for instance. I'm really sorry about this. I don't know why it's not. I would like, and that was what you will see when the next slide comes. To talk a little bit about the ear and in particular cochlear hearing loss. We don't have time to talk about all the things that can happen to your hearing or your ear. We have the outer ear where sound is transmitted to the eardrum, where the sound is changed or transferred into mechanical vibrations in the bones in the middle ear. And then we have the cochlea, which is the sort of sensory organ for hearing. There the mechanical vibrations are transferred into electrical signals in the auditory nerve, and the signals are brought up to the brain. And here I will be focusing on cochlear hearing loss. It's sometimes called sensory neural hearing loss. because it's not just in the cochlea that the things can go wrong, but also in the connection to the nerve fibers. And the common causes for cochlear hearing loss is aging, noise, or acoustic trauma, or ototoxic drugs. There are also other factors, but these are some of the most important or commonly occurring. I should not have practiced my presentation, but patience, I think. So I will talk about some of the consequences of cochlear hearing loss. And the most obvious one is that the audibility is reduced, so that a person with a cochlear hearing loss has a raised threshold for hearing. And that is basically what we call a hearing loss, that people can't hear soft sounds. But a cochlear hearing loss is also associated with a differing loudness perception and a reduced dynamic range. I will come back to that. Also problems with frequency selectivity to separate out components in a complex sound. And through out this presentation, when you see these small hearing aids, that will say something about hearing aid signal processing to alleviate some of the things that I'm talking about. Here is a closer look at the cochlea, and there are three ducts or canals running along the cochlea from the base to the apex, and the composition of the fluids inside those ducts is central for the transference through chemical reactions to a signal in the auditory nerve. What I wanted to talk about, which is central to how hearing aids work for cochlear hearing losses, is the fact that the cochlea functions as a frequency separator or frequency analyzer. So this is the cochlea sort of uncoiled. So here is the base where it's connected to one of the hearing bones, and here is the apex. And a central part is the basilar membrane, which separates the two lowest ducts or canals. And that has specific properties that help with this frequency analyzing in the cochlea. So at the base, the basilar membrane is narrow and thick. And at the apex, the basilar membrane is much wider and more flexible. And in occurrence with other things, when you talk about resonance and so, it means that sounds of lower frequencies will be coded higher up in the cochlea towards the apex, whereas high frequency sounds will be coded down towards the base. And if we look at how that coding happens, we can look at this figure, so we can see that the distance here is the base, and up here is the apex. We can see that the low frequencies are coded towards the apex, and the further down towards the base, the higher frequencies. And these are data from Bekesi, our Nobel laureate researcher in our field, who did lots of work on how hearing functions. And at that time in the 1940s, he could only make observations on cadavers, so on animals and perhaps also humans who did not live any longer. And he saw these sort of fairly broad pictures of how the basilar membrane helped with the mechanical frequency analysis. But it looks quite different when we now, with other equipment, can look at the basilar membrane and the cochlea with all the physiological structures intact. So in the cochlea, we have two types of hair cells. We have one row in a human, one row of inner hair cells, and they are the transmitters of information from the cochlea up to the brainstem and the brain. But we also have 3 to 5 rows of outer hair cells, and they are mainly receiving information from the brainstem and the brain to the cochlea. And they provide an active and nonlinear feedback mechanism that can sharpen the tuning of these frequency curves that we saw. So it sharpens the frequency analysis, and it can enhance low-level signal components. the ones that makes it possible to hear low level sounds. And the outer hair cells are most easily damaged. So for milder hearing losses, it's quite common that the main reason for the hearing loss is damage to the outer hair cells. And this is a schematic picture of the difference between having only the mechanical part of the response and then having a healthy ear with all the outer hair cells functioning. So that you can see that there's a sharpening in the frequency analysis. I don't dare to say it, but now it's going well with the changes of the slides. And the first thing that we can look at is, of course, the loss of audibility. And that is normally depicted in an audiogram, as shown here, where 0 means average hearing thresholds for normal hearing young people. So in practice, we need higher sound pressure levels to reach the threshold, when you can just notice the sound in the low and high frequencies. But when we look at hearing loss, we compare it to the thresholds of normal hearing people. And this is a fairly typical hearing loss. It could be of cochlear type, and it could be because of age or noise. So we can see the loss of audibility, the raised thresholds, and we can see that it's not uniform over the frequency range. So that is actually something that we are quite good at in the hearing aid industry, to provide frequency-specific amplification. And here is just an example of some formulas you can use to calculate the gain needed for different types of hearing losses. And you can see that they are, for this audiogram that is inserted here, providing more gain in the high frequencies than in the low. But we don't want to sort of fully restore hearing thresholds, meaning that, for instance, for this person who has a hearing loss of 70 decibel hearing level at 4 kilohertz, we don't want to provide 70 dBs of gain, and I will explain why. If I, in the same audiogram, now plot something that is called the uncomfortable loudness level, so that's the level where people say, now it's too loud for me to listen to, it's uncomfortable. This is a realistic, uncomfortable loudness level sort of profile for a person with this hearing loss. It's also exactly what could be expected for a normal hearing person. So whereas a normal hearing person at 4 kilohertz has a dynamic range from threshold to uncomfortable of a little bit more than 100 decibels, this person has a dynamic range from 70 to 105. So it's considerably reduced, and it means that the hearing aid has the task of providing soft sounds close to the threshold, but make sure that the sounds are not excessive, so that they will pass by the uncomfortable loudness. And in hearing aids, we have the following strategy, or one of the strategies we can have is to normalize the loudness. So it means that if this is the unity line, and we look at the input levels, so for low input levels, we provide a lot of gain, and for higher input levels, we provide less gain. And for this example, which is not too different from the audiogram, then when the sound is high enough, sound level is high enough, then no gain is needed. And then we can add some output limiting because we can in the hearing aids. So that is something that is done in hearing aids, and even if it sounds straightforward, there are some aspects about how quickly this should be done, the adjustment of the gain and so on, and in how many frequency channels it should be done and so on. But this is also something that is done in modern hearing aids. Then I wanted to talk about masking, because that's what it says on the header there. And I will, for simplicity, use a model from the 1940s by Harvey Fletcher, where he said that we can think about the peripheral hearing system as a filter bank of overlapping bandpass filters. And if we want to detect a tone in background noise, the matching filter is used. So if it's a tone of 1 kilohertz, then the filter surrounding that part of the basilar membrane, I mean, it's not a filter as such, but it functions as a filter, is used to detect that tone. And central is that the only noise components that pass through this filter contributes to masking of the tone. And if you have broader auditory filters, it means that the masking effect is larger because more can fit into that filter. And that is exactly what happens as a consequence of cochlear hearing loss, or in particular outer hair cell loss. So whereas the auditory filters of the normal ear looks like this, this is measurements and calculations done for an impaired ear. You can see that the filters are considerably broader, which means that there will be more background noise coming through and masking that signal. And in a worst case scenario for speech sounds, people with a cochlear hearing damage might need the SNR to be more than 20 dB higher than for normal hearing people, which is a lot. And now it becomes more and more difficult with the hearing aid part. So what can be done in hearing aids? What we do use is noise reduction of various types, and you know probably more about noise reduction than I do, but that is something that has been used in hearing aids for a long time. The other thing we can do is to use directional microphones so that you have an increased sensitivity ahead of a listener and decreased sensitivity from the back. That works well in the lab where you have a damped room, not lots of reflections. And you can also, when you know the characteristics of the directional microphones, you could also cheat a little bit and place the background noise where the sensitivity is the least. But in everyday life, users usually notice very little difference when the directional microphones are on. And that is because if you are in a room with some reverberation, then it's not just a direct sound that is reaching you. Experiments have been done with more extreme beamformers, and they provide a stronger directional benefit, but you also have difficulties with the environmental awareness. It's almost like you put blinders on a horse and you can sort of hear just in front of you, but perhaps not what's happening around you. And I will come back to that. More effective, but perhaps a bit more cumbersome, is to use some external microphones placed close to the talker, and then you can increase the signal-to-noise ratio substantially. I also have a list of other consequences of cochlear hearing loss. And it's an interesting list, but I just, because I need to save some time because of my problems to begin with, I suggest that you read a paper by Brian Moore. It's now a little bit old, but it's a good introduction to the perceptual consequences of cochlear hearing loss. I also wanted to say something about other important aspects of hearing aid signal processing. And I'm using this schematic. I mean, we have the signal processing. I will come back to that. But we also have the situation that sound can be transmitted, for instance, now when I'm talking, directly into the cavity behind this ear insert that is depicted here. And that will create an unpleasant sound, and we call it occlusion. And you can try it by just vocalizing by covering your ears. And the way to deal with occlusion is to have a ventilated ear mode, or an open ear mode, which has become very well used these days. But then you lose some of the low frequency amplified sounds because that will leak out, and it improves the risk, or increases the risk of acoustic feedback. And feedback is the other thing, that sound can also be leaking out. That's number 5 here. And then be picked up by the microphone again and create acoustic feedback. Digital feedback reduction in hearing aids have been very successful and has given the opportunity to have open fittings. And then another aspect of the signal processing is the time it takes for the signal processing and the group delay. A group delay of 3 to 5 milliseconds is often noticeable, and delays longer than 10 milliseconds are almost always objectionable. And we have a particular problem with the delay for open fittings, because then the processed sound, which has taken a little bit longer, and the direct sound that is leaking in through the ventilation, they are mixing with each other and are out of phase and can create sound that doesn't sound so pleasant. So what about speech again? This will be a talk about what's happening with speech, but also a sort of almost like a summary. So how do we hear in complex situations? And the situation I'm thinking about is a fairly large group of people in a conversation in a noisy pub, for instance. People know each other, so they are not so strict with turn taking when they talk, and the talkers and topics change quickly. And how can we cope in that situation? And this slide and the next is inspired by a paper by Shin, Cunningham and Best. What we want to do is to enhance the source of interest and suppress other sources, but we still want to maintain some environmental awareness for rapid refocusing. So first I might focus on a person to my left, and how do I do that? But suddenly someone mentions my name, and then I need to refocus. And there are some theories related to this, and it's interesting. The first, sometimes it's called auditory scene analysis, what is done in the hearing aid, and it includes the formation of auditory objects and streams, and that is formed by looking at the spectrotemporal structure of various sounds. Common onset is an indication that these sounds belong to the same object. You often listen to timbre, so if people are talking with both different pitch but also different timbre, and you relate those to one object or one stream of sounds. Location is a strong indicator for if you have a person talking to your left, that person will not very quickly start talking from your right. So you group sounds from different locations together. And this formation of auditory objects is more effective over time. Then you also need to select the auditory objects that you want to attend to. And then the attributes, then you need to have attributes that distinguish a certain sound from other sounds. And then it's important with the switching of attention. And especially if the selective attention takes a long time, the situation will be considered challenging. And the more people who participate in a conversation, the more rapid and unpredictable the required switches need to be. So if we look at these three sections and see what happens when you have a hearing impairment, we have talked about hearing impaired or people with cochlear implant having a reduced spectral and temporal acuity. They have broader than normal frequency selectivity, and it means that they have fewer independent frequency channels to derive information from. They have an increased masking effect, and therefore the formation of objects is slower than for a normal hearing person. The top-down processing that you can use to repair when you have difficulties with the formation has less information to work with. And unfortunately, hearing impaired people also have less benefit from differences in spatial location than normal hearing people have. So slow formation of objects and streams, you miss portions of sound, and it's especially problematic when attention must switch rapidly. And these repair mechanisms can drain your cognitive resources connected to one of the hypothesis for hearing loss and the connection between hearing loss and dementia, and it can lead to tiredness. And for hearing aids, we have noise reduction that we can work with, directional microphones, but we have difficulties with the directional microphones. So in summary, cochlear hearing loss affects audibility and loudness perception, leads to broader auditory filters, and that can lead to problems with masking and object formation. And with the signal processing, we want to enhance the targeted speaker, suppress the other sounds, still with good sound quality. And we want to be able to switch attention between speakers, but we still want to hear the environment as well. I thank you for your attention.